Okay, so we will move on to an important class, which is we talk about is Maillard reaction. So we call it protein section 2, which is called the Maillard reaction. Maillard reaction. So what is Maillard reaction? This is named by Louis Maillard in 1912, a French chemist. He found glucose reacted with glycine in the heated environments turns brownish color. So what this tells us, Maillard reaction is a non-enzymatic browning. So it is a non-enzymatic browning. We need to go ahead to first of all review what is called enzymatic browning. Okay, so enzymatic browning, what is that? This is, we can explain to you is if you have an apple, okay, you have apple, and you cut it in half, you put at room temperature for about like half an hour. What will happen? It turns brownish color. This is called enzymatic browning. And the enzymatic browning, there's a reaction which is polyphenol reacted with polyphenol oxidase, then become melanin. That is a brownish color. So why we call it enzymatic? Because we have oxidase. Okay, that's an enzymatic. A Maillard reaction, there's no enzymatic. So what is Maillard reaction? If we said very simple, using a general equation, it is reducing sugar with amino acids going through polymerization together with condensation and generate a polymer. And this polymer is melanoidin. And that is showing you also brownish color. And that is called the Maillard reaction. Now, something we want to talk about that these amino acids in a food products, there could be free amino acids or are components of protein. Or we said very broadly, there could be some nitrogen containing compounds. Okay, so this is Maillard reaction. We're going to go back to talk another thing, the reducing sugar. Okay, but we talked this one first. Now, Maillard reaction. obviously will give you some good advantage. Give you a special color, a special flavor, a special aroma. We all know that. So for example, you have chips, French fries, you have steaks, you have chocolate, you also have peanuts. Those are the results of the Maillard reaction. But Maillard reaction also going to give you some bad things. What happened? It couldn't make it shorter shelf life. So a very common example is you have a milk powder. A milk powder is the most prolific component is lysine. Okay, the lysine is gone or decreased, then turns to yellow color. Now obviously another one is the nutrients is decreased. Nutrients value we can say decreased. Now another thing we also want to say, Maillard reaction happened at the extended heat temperature. They will also could generate carcinogen or carcinogen chemical. For example, acrylamide. And we're going to talk about this detail, okay? So this is the opening remarks for Maillard reaction. But we have one thing we haven't mentioned, the reducing sugar. So this is something we want to emphasize here. What is reducing sugar? If you are master degree students or PhD degree students, and Dr. Martok is your committee, she always will ask you what is reducing sugar. So we want to talk this concept first. You may know it, but you may not know from the chemistry standpoint. So reducing sugar, we know glucose, lactose, maltose, lots of them are reducing sugar. So what this means? Okay, I have a glucose. Let's draw a glucose structure. We're going to draw it a couple of times today. So H, OH, H, OH, OH, H, H, OH, H, CH2, OH. Okay, we have a glucose. The glucose, if the ring is open, what will happen? This will become, I'll draw it briefly, CHO. If the ring is open, the CHO will be exposed. This is, we call it a aldehyde group. So therefore, the structure here from the chemistry, we call it semi-acidyl. So it's a reducing sugar because aldehyde will generate, and it's a semi-acidyl. So that's glucose example. Okay, let's give another example, is lactose. So what are the two components of lactose? Lactose is component by glucose and galactose. And the components they combine is very simple. And the structure for glucose and galactose is also very similar. The only difference is this carbon number 5, one is up, one is down. Okay, so we just draw it right here. So we have H, OH, H, OH, this is OH, H, this is down. So H, OH, H, CH2, OH, So how they connected? Right here they connected. They connected with O. And this is 1 prime, this is 4 prime. So for lactose, it is connected is 1 prime, 4 prime, glycosidic bond. And here you see it is also semi-acetyl. If the ring is open, it will become CHO, that's aldehyde. Okay, that is a reducing sugar. Okay, there is an exception. A very important sugar in the world, and even we thought it's a table sugar, is sucrose. And sucrose is not a reducing sugar. This you should know, and you already know, I know. But what's the reason? It's not a reducing sugar. What's the reason? So you need to know what is sucrose because combined. Sucrose is combined with glucose and fructose. So let's draw here a glucose again. We're going to draw all the time glucose structure, okay? Because we're going to have to explain to you what happened. So this is a glucose. Now what is a sucrose looks like? Sucrose is here. It's a little bit different. So you go here, you have HOH, CH2OH. Then you have HOH, OH, H. And remember this is H, CH2OH. We talk about 1,6 fructose, 1,6 biphosphate. We reviewed about that. So this is glucose. And this is sucrose. Oh, sorry, this is a fructose. This is a fructose. Okay, so sucrose is combined by glucose and fructose. How do they combine? That is 1 prime, 2 prime glycosidic bonds. And what is this one we call? That's a acyl. It's not hemiacetal. So what it means, there is no free aldehyde generated. So it is not a reducing sugar. Now how are you going to remind it? For glucose combined with galactose become lactose, it is 1,4 glycosidic bond. We call the connection is head to tail. That's 1,4 glycosidic bonds. For sucrose, it is glucose with fructose, it's 1,2 glycosidic bonds. We call it head to head connection. So it is not a reducing sugar. But then there is a question comes out. Sucrose is a table sugar. It widely exists in lots of the products. But how come the products have sucrose still can go through Maillard reaction? The reason is they break down first. They break down, become glucose or fructose, those are reducing sugar, and then they go ahead to happen the Maillard reaction. Okay? So keep in mind the key thing for reducing sugar is somehow the ring opens, they will have a free available aldehyde. Otherwise, it is not a reducing sugar. And the typical example is sucrose. Okay, so this is something we talked. Okay, now we're gonna get back to talk about the detail of the Maillard reaction. Okay, Maillard reaction, it is relatively say it's a complicated chemistry reaction. Here and there, lots of the textbook or journal article talk about that. So far what we have is Dr. John Hodge. Dr. John Hodge is a research chemist worked at USDA ALS at Illinois. He did a lot of research by himself. He also did a literature review. He comes out with a detailed explanation. What is Maillard reaction, including all the chemical reaction. Therefore, Maillard reaction, we call it Hodge-Maillard reaction. And the explanation, the procedure by Dr. John Hodge, we call it Hodge schedule. And there's a paper published at the Journal of Agriculture and Food Chemistry. It's not a big journal, not a Nature Science. A paper is cited more than 800 to more than 1,000 times. And remember, the area is no computer and no internet. So that's a great achievement. So what is Hodge schedule talks about? It is starting from aldose. So starting from aldose, let's say a good example is D-glucose. Okay, an aldose comes out. It's reacted with a free amino acids group. Will become a first product is called in substituted glucosamine. We're gonna have the structure for you how it happens, okay? Then will generate 1' deoxy, 1' deoxy, 1' amino ketone CME. Okay, sorry. 1 amino will generate 1 amino, 1 deoxy, ketone CME. This product have another name, which is called Amaduri rearrangement. Okay, once the 1 amino, 1 deoxyketone CME created, the things become complicated. It depends different situation. At a pH around 4 to 7, which is slight acid environments, it will going through the procedure called 1,2 enolization. Okay, and then at the pH more than 7, it will generate another reaction called 2,3 enolization. 1,2 enolization at a pH 4 and 7 will generate a product called HMF. Hydroxyhydromethylfurfural. 2,3 enolization will generate products called reductase. That's at pH 7. Now, what happens is, if the reductase somehow in the food products meet with the alpha amino acids, which is the amino acids widely exist in the food products, they could going through a process right here called Strecker degradation. The Strecker degradation will generate multiple modified aldehyde. Now, if the products, what happened during the processing is in a very high temperature or extremely high temperature, they will directly generate fission products or volatile compounds. Let's say dicarbonate. Let's say pyruvate aldehyde, like that. Okay, so that is the second stage. Okay, last stage, third stage, last stage. All these products, they could be working with the imine in the further product, with water, with carbon dioxide and others, going through polymerization and condensation, generate a polymer called Millard. It is a polymer. So this is Dr. John Hodge's schedule. In the scientific area, we were very clear about here. The free amino acids work with aldose, become N-substitute glucosamine. We also very clear about how we generate one amino, one deoxyketosamine called amadular rearrangement. We kind of okay around here, like Strecker degradation, 1,2 enolization, 2,3 enolization. We kind of good at that, but we don't know what happened right here. This is a big question, because in a food products, it's so many ingredients. So we don't know, it's a product by product based analysis. We don't have a uniform equation or specific reaction for that. It is only a conclusion. And we don't even detail knows what happens really here. Okay, so that is the overall picture of the Millard reaction. Now, I wanted to tell you that the textbook is a little confusing. The textbook from Domain, the green one, I said the a little bit easy one, the introduction of the food chemistry. What they talk about is this line. They talk about this right here. That is by Domain book. The chapter is talk about here. That's why you read here and there, it's a little bit confusing because they only talk about one line. Now in Dr. Fenneman's book, the heavy one, we call it the Bible of food chemistry. They talk 1,2 they talk about 2,3 mineralization in the carbohydrates, which is the sugar section. That's little. And then the strict degradation is somehow in the other chapters. So makes you a little confusing, and here and there, it's everywhere. And I understand the editor's point is from a different perspective to explain the Maillard reaction. Okay, so that's why a little bit confusing. Now, in your chemistry class, let's say general chemistry class, chemistry 101, you may just talk about N-substitute glucosamine amadular rearrangements, then all of a sudden become melanoidin. So that's a general chemistry class talk about. It doesn't go very detailed. So since it's for chemistry class, we're gonna go a little bit detail about these reactions. Okay, so the next one, we're gonna have this whole blackboard, we're gonna talk about this, how they happen. So we're gonna talk about all these chemistry reactions. So first of all, we still go back to glucose. Okay, we have glucose. The glucose looks like this. Now we know the ring. Six carbon ring, we draw all the time. To let you be familiar with that, we'll talk again at the carbohydrate section. This ring, this one, we call it a Fischer configuration. If the Fischer configuration existing in food products, it could happen Maillard reaction, but it's not that easy. What the easiest one happen is gonna have an open ring. So what it's gonna be looks like is CHO, CH, OH, CH, OH, CH, OH, CH, OH, then CH2, OH. What I didn't pay much attention here is I put H and OH on the same side. So I don't care about D or L isomerization. Okay, that's another topic we'll talk about later. So you have to become this open ring. Open ring structure is easily to have Maillard reaction. We can label them is carbon number 1, number 2, 3, 4, 5, and 6. Okay, so it's like that. And on the top, this carbon 1, we should also, you guys should know, this should be written as H, like that. A proton and a carbonyl, okay? Carbonyl, like that. Now, we have amino acid coming. So, all NH2. Amino acid happen. It's gonna attacking the carbon number 1. So what's the carbon number 1 will looks like? Will be CH, OH. Okay, carbon number 1 goes there, and here is ONH. CH, OH, ONH. Yep, it's very simple. So we go here, CH, OH, CH, OH. These are the same. Not touched yet. CHOH, CH2, OH. What is this one? N-substitute glucosamine. Substitute glucosamine. That's the first step. Okay, then the second one, what we gonna happen? This is something we talked about before. We'll remind you. They will lose water. Still happening, carbon number 1, they will lose water. Once they lose water, what will happen? on the top, it will become CH double bonds ON. That's on the top, okay? Here all the same, CH, OH, CH, OH, CH, OH, CH, OH, CH2, OH. What is this one called? This is a shift base. Okay, once the shift base happens, next one, we go a little bit easy. We're not gonna go very complicated. During this process, we could happen adding protonation. We could lose protonation. We also could working with a water or with some imine group and going through isomerization will generate our next important products is CH2 or NH, CH, OH, CH, OH, CH, OH, CH2, OH. What is this one called? Right here. That's called 1-amino, 1-deoxy ketone thiamine. If we use glucose as an example, this is 1-amino, 1-deoxy D-fructose. Fructose is a ketose, it's not an aldose. So, that's right here. So we finished talking from here to here, it's pretty clear. Here something we want to mention is that, you see lose water here? This is the reason why at the beginning we talk about the water. Remember the curve? What is the Maillard reaction will happen? Is in this one. So water activity somehow is 0.25 to 0.75. More accuracy is 0.6 to 0.7. That's why the Maillard reaction curve looks like this. That is the range for milk powder. And you will see during the reaction, lots of the time is lose water. So they don't want the products to have too much of the water. And here, which is expressed as a water activity, or we say equilibrium relatively humidity. Okay, so that's 1-amino, 1-deoxyketothiamine. Another thing I want to mention is in the textbook, but it's kind of confusing. Start from beginning to here. It all happens is carbon number 1. So, carbon number 1, we call a medullary rearrangement. But is that could be happen on the other end? Is carbon number 6? That could be happen? Yes, it could be. If something happened for carbon number 6, it will also go through a similar but different biochemical reaction. We call it Haynes rearrangement, OEC. In the textbook, it's mentioned very briefly. Just want to tell you, 1' and 6', head and tail both could happen. 1' carbon is a medullary rearrangement, generate the ketone thiamine. If it Haynes reaction happens, it will have aldo CME. And we skip that. We don't talk about that here, too much detail, okay? Okay, so we have this product. Let's draw it again. CH2 or NH. Then you go here, CO. Then we have CHOH, 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 CH2OH. So we're going to talk about here all these things. First one, at pH less than 427, we're going through 1,2 enolization. What is 1,2 enolization talks about? One-to enolization is this proton gonna attacking here, attacking this carbonyl group. So once it's attacking here, what will happen? This becomes OH. Okay, you see the carbonyl group have a double bond? If the proton goes here, it becomes OH, becomes a hydroxy bond. Obviously, this becomes double bonds. So CH or NH. The others are the same, okay? CH, OH. Not yet, we'll get to that. They'll touch. They have not joined the reaction yet. What is this called? 1,2 NO amino. Okay? The second is what will happen. Once these things happened, at carbon number 3, they will lose. They will at carbon number 3. Let me double check. This OH, that's correct. At carbon number 3. They will lose this guy. We call beta elimination of hydroxy bonds. But it's not happened alone. It happened is lose water, but adding proton. Therefore, overall become beta elimination of hydroxy bonds. So what it looks like when this is gone, what it looks like. Obviously this become a double bonds. Is that right? What this one gonna go? So what it gonna looks like? CH, double bonds, or NH. Then you go here, COH. Then you go here, double bonds, CH. Then here are the same. CH, OH, CH, OH, CH2, OH. What is this called? 2 primes, 3 prime. Simple 2 primes, 3 prime. NO. Okay, now you see. This goes here. This amino group is at the top with the double bonds with CH. If you know a little bit of chemistry reaction principle, the energy to break down that RNH is very low. Very similar to what we talk about the hydrogen bonds. It's only like 5 kJ per mole can break it. Therefore, what it looks like, this is gone. Okay. Now in the food products, also we're going to have protonation. We also have H2, some isomerization. What will be generated products? CH, CH, CH2 here are all the same. CH2OH. What is this product called? 3' deoxyoscellulose. Okay, now this is gonna lose water. Happens right here. So water gonna go. Okay, gonna lose water. Now what's the structure looks like? This is a simple aldehyde group. We have CH. So you go here, we have CH, double bonds, CH. Then you go here, CH, OH, CH2OH. Just want to make sure what I'm writing is correct. Okay? Don't want to be, yeah, CH, that's correct. What is this called? Also close. Okay, when you see here, what will happen? Continue to lose water. So next one, continue to lose water. Then become a structure is very interesting. We go here, CH, go CH, go C. And this doesn't do, CH2OH. This is a transition step, a carbonyl ring. The carbonyl ring is not stable. It's going to do a modification, we call it isomerization. It's going to go isomerization. And people understand easily, it will become the products. Looks like this. CHO, carbonyl is there, aldehyde is there, CH2OH. What is this guy? This guy is HMF. That is, this OH is hydro, okay? That's methyl. CH3 is methyl. OH connected to CH2 is methyl. Hydroxy methyl furfural. Acronym HMF. So this whole process to here, yes, 1,2 enolization. It contributes major for the color change and slightly for the flavor and aroma, slightly. Major is for color change. That's 1,2 enolization. Okay, let's talk about 2,3 enolization. What it looks like. We're gonna have to draw on the top. So 2,3 enolization. We're gonna borrow this guy. Okay. 2', 3' enolization. Since it's called 2,3 enolization, obviously, carbon number 1, carbon number 2, carbon number 3, it's gonna happen is in carbon number 2 and carbon number 3. They first will do a rearrangement. So let's just draw like this. How they rearrange? COH, C, OH. Don't forget the double bond. Okay? Now, CHOH, CHOH, CH2OH. This is a transition step, doesn't have really a name for that. At this stage, this is gone. This is gonna go. Okay, I wanna make sure this whole thing is gone. When this whole thing is gone, on the top becomes CH3. What is this called? 1-methyl 2,3-dicarbonyl. Two carbonyl in the middle, methyl group on the end. It's not stable. Something gonna happen right here. But it's equivalent, equilibrium, balanced during the food products. So we draw this, we draw that. What will happen is CH3. If something happened there in the middle, OH, COH. Don't forget the double bonds right here. Then CHOH, CH2OH. What is this called? Hydroxyreductone. This is a reductone. So in the food products, they could be coexistent 1-methyl 2,3-dicarbonyl and hydroxyreductone. And those products together